We are probably all aware of various examples of RL performing really well in simulation, whether this is various, Mojoku or robotic manipulation tasks, game playing, things like Atari, Go, these sorts of things, or even I think we can think about things like RLHF and LLMs as effectively doing sort of an optimization in a simulated environment. And these examples really show that training in simulation we can learn powerful general behaviors from scratch using RL. We can basically put in an algorithm with a reward function, just set it running, and it will optimize the reward function and will learn powerful behaviors that often reach superhuman performance. And while these examples are really cool, and it can learn this performance, this sort of comes at the cost of a large number of samples. And so most of the examples that are showing here, as well as just RL and Sim broadly, you're talking at least millions, if not significantly more interactions. And so the sort of standard paradigm of training RL and Sim just kind of basically lets the agent go, lets the algorithm go, and it collects a ton of samples. And as it collects all these samples, then it figures out how to optimize the reward. But this collection of large amount of samples is pretty critical. There's sort of few examples of learning really powerful RL behaviors or behaviors with RL without sort of this large sample complexity. Now, there's a lot of problems where we might want to apply RL to in the real world. In particular, I'm talking about sort of real world control type settings, say various robotic manipulation or locomotion tasks. And while we have seen RL applied to these problems, and we actually have seen it applied successfully to these problems, the examples that we see of RL performing well in real-world settings typically either require a very sort of constrained set of tasks, say limited, simple, short horizon tasks, or they require a lot of human engineering, whether that means reward engineering, designing reward functions that are easy to learn on, providing a lot of human demonstrations to bootstrap the RL process, or something else. And so while RL can work in the real world, we are really not seeing the sort of general powerful behaviors being learned with RL when deployed in the real world as we see in simulation. And of course, the challenge here, the reason for this primarily is that uh, it's usually impractical to collect millions and millions and millions of interactions online in the real world. So while I could deploy a robot for weeks and just have it try different things and collect a bunch of interactions and then figure out how to optimize the reward, in most practical settings, this isn't really something I'm going to do. It's just going to take too long. It's going to be too expensive. And so when we go to apply RL in the real world, we just aren't able to get the same level of performance that we often can get when applying RL in simulation. Now, this sort of dichotomy, this sort of difference we see between deploying RL in simulation versus RL in the real world has spawned a lot of work in what we'd call sim to real transfer. What this means essentially is usually you do something like the following. When you train a policy with RL in a simulator to accomplish some task. And okay, so for example, say it's a robotic task, you train the agent to pick up a beam and stack it on some blocks in simulation. Now you hope that this simulator is a faithful representation of the world, and then you take your policy, train in simulation, and you go and deploy it in the real world. Now, if everything works out, you get the following behavior. Basically, the robot will also solve the task in the real world. However, this isn't actually what you see all the time, and very often you might see something like the following. The robot will try to solve the task. Maybe it does something reasonable, but it won't actually solve the task, right? It sort of picks up the beam in the wrong spot. It can't actually properly stack it. And the reason for this is that when you are training a simulation and deploying in the real world, you're always going to have some gap between the sim and the real. It's sort of incredibly difficult to completely eliminate the gap between your simulator and the real world. Modeling the real world is hard. Getting a perfect representation of the real world in simulation is hard. And usually you just simply can't do that. And so with sim to real, while it might work in some settings if you have a very good simulator or a simple task, often sim to real transfer fails due to this gap between sim and real, due to the modeling difficulties of modeling the real world in simulation. Okay, and so while sim to real transfer sort of might be able to sort of bridge this gap between performance in sim, of RL and sim and performance in real, we really are not seeing, to a large extent, maybe the success of sim to real that we would like to see. Okay, and so with this talk, what I'm going to focus on is really trying to understand this question of how to utilize simulators. So how can we best utilize a simulator to speed up real-world RL, in particular in settings where there's some large sim to real gap, right? If my policy transfer from sim to real is not succeeding directly, how can I still use my simulator to speed up that process of real-world learning? I'll break the talk up into two parts. In the first part, I'll talk about what I call the unrealizable setting. This is a setting where the simulator cannot represent the real world perfectly. There's some irreducible gap. And in part two, time permitting, I'll talk about I'll talk about the realizable setting, where I assume that we can actually model the real world effectively in simulation, but to do that, we need to learn some unknown parameters. Okay, and what we'll actually see in both of these settings, the sort of the key takeaway of this talk will be the following: that it's easier to learn to explore than to learn to solve the task. So while I can often, if I try to solve the task in sim and transfer that to real, that might fail. I can often actually learn behaviors in sim that are useful for collecting informative observations in the real world, and then use the data they collect to learn to solve the task in the real world. Okay, so before I dive in, I'm just going to give a few sort of just preliminaries in terms of like what this setting looks like. So we'll denote the real world, some environment, call it mreal. And that will be, you can think of some sort of robotic task or whatever. We'll then also assume access to some simulator, we call msim, which we assume is in somewhat a faithful representation of the real world. Now, the advantage of sim is that the samples we assume are effectively free. So we don't really actually care about reducing sample complexity in sim. We just assume we can spend a lot of samples learning behaviors in sim. But then there is some fundamental mismatch between sim and real. So while sim might correspond to real in some way, it's not able to perfectly represent it. And I'll be more precise in the following what this mismatch looks like. Okay, we'll assume also that msim and mreal are Markov decision processes. And the sort of goal formally then is to just maximize some reward R in mreal. We'll denote by P the transition function. We'll denote by H the length of the horizon, which we assume is finite. And we'll assume that there's a finite number of actions, which we denote as A. And then sort of standard in RL, we'll let V pi denote the value function, and V naught pi the expected reward of policy pi, and V naught star the value of the optimal policy. And also just throughout, I'll be using superscripts of sim and real to designate which environment something corresponds to. For example, P real corresponds to the transitions for real. Okay, so this is kind of the motivation in this setup. Any questions on this before I dive into the details? Okay, cool. So we'll first start in this sim to real transfer without realizability, where there's this irreducible gap between my sim and the real. This is based on a paper we presented in NeurIPS this past December, and it's collaborated with several different people, but I want to in particular highlight Kevin, who did a lot of the experiments I'll show you, as well as Abhishek, who sort of was the main advisor on this project. Okay, so a little bit more notation, a little bit more preliminary. So in terms of the modeling assumptions we need to make here, we need to formalize what do we mean by the centrial gap. Okay, we can't just say it's an arbitrary gap. In that case, you probably can't do anything. So what we'll do is we'll assume the following. We'll assume that there exists some value epsilon sim such that at any state in action, the transition probabilities for real and sim, the total variation distance between these transition probabilities is bounded by epsilon sim. Okay, we don't assume epsilon sim is known. We just assume there exists some such epsilon sim and that they're close in this sense. Okay, so you could imagine other types of mismatch, whether that's visual mismatch or something else. This is really dynamics mismatch. And that's really what we're going to be focusing on in this part of the talk. Although it's actually, if you talk to roboticists, this is often actually in practice what the real challenge is, right? Contact dynamics are hard to model and things like that. And so this is often actually the practical difference between sim and real. Okay, so this is going to be sort of a key modeling assumption relating sim to real. Now we'll also assume, to enable us to prove things about this setting, that our MDP has some nice structure. In particular, we'll assume that both mreal and msim are low-rank MDPs. For those not familiar with this setting, this basically just means that the probability transitions in my MDP are sort of an inner product of some feature vector phi of SA and some measure mu. Okay, and so the sort of takeaways, basically, you can decompose your MDP in some sort of linear fashion, and this allows us to learn efficiently over feature space. This is a fairly canonical setting in the RL literature. And we'll assume that phi is known for sim, so we know the feature vector for sim, but we don't know this feature vector for real, and in particular, these could be different, and in general will be different. Okay, so there just exists some linear parameterization of both real and sim, but it may not be the same linear parameterization. Okay, we'll also assume that we have some Q function class, call it script f, for which Bellman completeness holds, and every feature direction in phi is reachable. Every feature direction in MSIM is reachable. Okay, so MSIM has some featureization phi. We assume we can sort of cover the space of phi. We can visit states that reach every possible feature direction in SIM. Okay, so in this setting, then, our goal will simply be the pack RL objective. Okay, so learn a policy in MReal that is epsilon optimal in MReal, probability 1 minus delta, and do this by using the smallest number of samples from MReal possible. Okay, we want to maximize the reward in real, and we want to do this by using as few samples from real as possible. Now, we're working in the low-rank MDP setting, and it's known actually that low-rank MDPs are efficiently solvable, or solvable in a polynomial number of steps. And so you might say, well, you don't actually need your simulator. You can actually solve a low-rank MDP without using any sort of simulator or side knowledge in a polynomial number of steps. The issue here is that the algorithms that do this are typically all these theory algorithms, which require optimization oracles and other assumptions that are not satisfied in practice. And so while in principle you can solve a low-rank MDP efficiently, to do this requires optimization oracles that nobody is using in, say, the deep RL world. For example, like complex MLE oracles. And so what we're going to actually focus on in this setting then is ignoring these sort of impractical oracles that aren't used in practice. Can a simulator enable efficient learning with only simple practical oracles similar to what people are using in practice? So what I mean by that formally then is we'll just assume access to the following, a regression oracle, such that over my Q function class, I can solve a regression, means like a least squares regression problem. Now, this is like basically what people do in deep RL when they say like fit their critic, right? You just sort of optimize your neural network to minimize some loss. So we're just assuming the ability to do this, to minimize sort of some function with respect to like a least squares loss. Okay, so this is an oracle which is practical. People actually are using in deep RL. And then we'll also assume access to what we call a sim policy optimization oracle. Basically, for any reward function r tilde, we assume we can compute the optimal policy in MSIM for r tilde. And this is also, I think, reasonable in the sense that for a simulator, again, samples are cheap. We can just run our favorite algorithm for a long time, and eventually we will actually learn to optimize this reward. So this is also, I think, actually a fairly practical assumption. People can actually do this in practice reasonably well. Now, the thing to note here is that under simply this regression oracle assumption, this is not sufficient to solve low-rank MDPs. So if you just apply your regression oracle, you'll require exponentially many samples in the horizon length to solve your low-rank MDP. So alone, this regression oracle assumption is not enough. And so what we're going to try to understand then is if I augment this regression oracle assumption with my simulator and this sim policy optimization oracle, is this enough to efficiently learn in my real environment? Okay. Any questions on the setup?
Difference in the classroom? No.
Sorry, what was that?
Quick question. So when you are counting the samples, are you going to be counting the samples only from the real, or are you counting the samples from the sim plus the real?
Yeah, so the result I will show is only samples from real. However, samples from sim are also polynomial, basically. So basically the goal is to get like a good sample complexity in real while only using a polynomial number of samples in sim. So we don't really care how big that polynomial term is, as long as it's some like polynomial term.
Okay, thanks.
Okay. So what can we say under these assumptions? Well, sort of the first result, this is actually very canonical. It's called a simulation lemma, and it's, this goes back like 20 years at least. And it just says if you have two MDPs that are mismatched, and the mismatch is in total variation distance by some term epsilon sim, and I take the optimal policy from one MDP, M sim, and I deploy it in the other, its suboptimality will be bounded by h squared the horizon times epsilon sim. So this just says that like actually if I transfer a policy from sim to real directly, I can already bound the suboptimality. Now, I think the issue here is that, so as long as the goal, we want to learn an epsilon optimal policy. So as long as epsilon is greater than h squared times epsilon sim, this is acceptable. But in the regime where this isn't the case, it's not. And I think this is actually important because in practice, you aren't seeing that this direct transfer will succeed. And so in practice, the sort of goal epsilon you usually care about is often not going to be larger than h squared times epsilon sim. Like the mismatch between sim and real is such that my direct transfer is not giving me a good enough policy. So while sort of you can say something naively about what this transfer will look like, I think this is actually not what you really care about in practice. And so what we really want to understand then is our simulator is useful for learning in the regime where epsilon is smaller than h squared times epsilon sim. Okay, and so for that setting, let's just think about first simple sort of the naive sim to real transfer. So again, what do we do for standard sim to real transfer? We'll take our policy optimization oracle, we'll find a policy in sim that maximizes the reward we care about, and we'll call that pi sim star. Then we'll play this policy in real. Maybe we'll augment this with some amount of random exploration, epsilon greedy, something of that flavor. And then we'll take the data we collect and we'll try to improve sim in some way, whether fine-tuning it using our regression oracle, something like that. Okay. And so this sort of thing would work based on the last slide. It can learn at least an h squared epsilon sim optimal policy, but can it do better than that? And so we have the following result. Basically, there exists a simulator, msim, in two real environments, mreal1 and mreal2, such that both of these real environments are consistent with msim, meaning they both satisfy the total variation assumption, but they have different epsilon sim optimal policies. And we can also show that if we run this above procedure of doing sort of the standard sim to real transfer, to learn a policy that's epsilon sim optimal in one of mreal1 and mreal2 will require an exponential number of samples. And so what this says is that the guarantee I showed on the last page is actually like tight up to horizon factors. If I want to learn a policy that is better than epsilon sim optimal, then direct transfer is not going to work. And even direct transfer augmented with epsilon greedy exploration and fine-tuning of my policy and these things that people are typically doing in practice for sim to real transfer is not going to work. That to sort of break through this epsilon sim barrier, I need an exponentially large number of samples. Okay, and this is again, this is not practical. Like you need if you require an exponentially number of large samples in real, this is not an algorithm that you're actually going to be able to run. Okay, and so this says that like basically sort of standard sim to real transfer, what people are doing in practice, is not sort of theoretically justified. Like you can find examples where this breaks down. Okay, and I think it's informative actually to understand for this why this breaks down. And so let's just like walk through a simple example. So what I'm showing here first is just a sim MDP. So I start in some state S1, and I'll transition to some state S1 or S2 based on which action I play. So there's two actions. One is in black, one is in blue. Each of these transitions occurs with probability 1. Okay, so if I take the blue action, I will go to S2 and I'll stay in S2 for all time. But I get a reward of 1 over 8 by taking the blue action. If I take the black action for all time, then I will stay in S1. And if I get to this final S1, I'll get a reward of 1/2. Now, the challenge is that the last transition out of S1, it's a stochastic transition. So you will transition to S1 with some probability, S2 with some probability. And we assume that the probability of transitioning to S2 is greater than that of transitioning to S1. Such that in sim, if I could transition from this S1 to this S1 with high probability, then that would be the optimal thing, because I could get a total reward of 1/2. But because this transition will transition to S2 with greater probability, it turns out this is a suboptimal thing. So it turns out in sim, the optimal policy always plays the blue action and just basically walks down S2, because the probability of getting to this reward of 1/2 is too low. Okay, so this is the sim. Now for the real, we're going to look at the exact same environment. The only thing we're going to change is the probability of this last transition. So now we're going to make the probability of transitioning from this S1 to this S1 much greater, meaning that if I actually were to just play action A1, there's actually a reasonable probability I would reach this S1 and get this reward of 1/2. And if further, we can sort of construct this such that the optimal policy in real is actually to take this path, to always play action A1. Okay, and so we see that in sim and real, the optimal policies actually differ quite significantly. In sim, the optimal policy always takes action A2, and real, the optimal policy always takes action A1. And so even though they differ only at this one state, this actually has a drastic impact on what the optimal behavior is. And importantly, then we see that, let's say I were to play the optimal policy in sim and real. To identify the optimal policy in real, I need to get to this state here and figure out that I can actually transition to this state with reasonable probability. But if I'm always taking the blue action, I will never reach there. If I'm taking the blue action most of the time, but sometimes taking an action randomly, I might reach there, but it'll take an exponentially large number of samples. And so this is basically why this transfer breaks down, is that by transferring the optimal sim policy, it might be very uninformative about what the optimal behavior is in real. And so if I just deploy this in real, I'm never going to actually figure out what the right behavior in real is. Okay, but can we do something a little bit better here? How, is there something we could transfer? So let's think about just the following policy, which instead of it's not an optimal policy necessarily, it's just some policy that will roll in by playing action A1. So say it rolls into this state S1, and then it plays action randomly or whatever. Now, we see if we transfer this policy, actually, it will behave identically in real. We will visit the exact same states because the sort of transitions up to this point don't differ at all. So if I were to transfer this policy from sim, it's not an optimal policy in sim, but if I transfer this to real and I run this in real, I'll actually get to a state that is very close to the optimal, the sort of state where I'm going to collect a lot of reward in real. And if I get to that state, then I can just sort of play random actions and I will actually figure out what the optimal thing to do is in real. And so the sort of key thing here is that while the optimal policy differs substantially from sim to real, the behavior of any fixed policy won't differ substantially. It can differ by a most effector of epsilon sim. And so in this example then, we could actually transfer basically this blue policy that just traverses the MDP. So rather than transferring an optimal policy, we can transfer a policy that traverses the MDP. And you can show actually in this example that this will work. So the question then is this more general, right? Okay, we showed that sim to real naively transferring the optimal policy doesn't work, but does something like this work? Does transferring sort of a high coverage policy work? And so we're going to propose the following algorithm, which does just this. So it'll train some set of policies, which I call pi_exp. And these policies, they're not optimal in sim, but they simply cover the feature space in sim. They're getting high state coverage in sim. So we can train these fully in sim, and it turns out you can also train these by using only the given oracles, the sort of least squares oracle and the sim policy optimization oracle. So we'll train these policies in sim, and then we'll play these policies in real, coupled with random exploration. And I'll be precise, or I'll explain the random exploration, how that works a little bit in the following. But for now, just think about we're going to take these policies we train in sim, we deploy these in real, we do some random exploration. Then we take the data we collected from this exploration in real, and we use our regression oracle to just fit a Q function to this data. And then we just return the sort of policy that maximizes this Q function. Okay, so this is it. This is basically the whole algorithm. It relies only on our computation oracles. In sim, you can solve for these high coverage policies using the sim policy optimization oracle. And then in real, all we need to do is we need to just run one iteration of our regression oracle. Okay, what can we say about this? So we prove the following theorem, that in this sort of general low-rank MDP setting, as long as epsilon sim is small enough, then with probability 1 minus delta, our algorithm finds an epsilon optimal policy in real using only a polynomial number of samples from real and a polynomial number of calls to the given oracle. So assuming, again, these oracles are efficient, this means that we also only take a polynomial number of samples in sim. So what does this say? Well, going back to what we showed previously, we showed that learning without a simulator requires an exponential number of samples. Direct sim to real transfer, even with fine-tuning and random exploration, also requires an exponential number of samples. But doing this sort of exploration policy transfer, transferring these exploratory policies from sim only requires a polynomial number of samples. And so this actually shows that there's sort of this exponential gap between the sort of standard sim to real practice that people are using and what we're proposing here of transferring these exploratory policies. And I'll just mention sort of this small enough. Basically, this just says that the simulator has to be close enough in some sense to allow for exploration policy transfer. If the simulator is totally unrelated to the real, then exploration policies won't transfer. You need some condition to get them to transfer, but in particular, this condition is independent of epsilon. So I can choose epsilon to be as small as I want, and it won't change what this condition requires. Epsilon sim could be much, much larger than epsilon in particular. Okay, so this is kind of the main punchline, at least of this first part, which is that if I want to use my sim effectively, I shouldn't use it to learn an optimal policy. I should use it to learn a high coverage policy or set of high coverage policies and transfer those. So I want to give a little intuition for why this works. I already gave some, but I think it's actually informative to think to sort of like show why this works, because it will actually help them motivate what we will do in practice. Okay, so to explain how this works, let's think about the following. Let's say we start in some state S naught, and we play our policies pi exp up to some state h. And let's denote the states that are visited by pi exp at step h by x of h, and we'll denote the states not visited by pi exp as bar x of h. Okay, so what we can actually show, and I'm not going to work through this here, but it's in the paper, is that if there's some state that is not visited by pi exp, then actually we can bound the total probability of transitioning into this set of states, bar x, by some value chi, which is less than 1. Sorry, this should actually be p real. This is the probability in real of transitioning to bar x of h is bounded by some value chi that is less than 1. Now, chi depends on epsilon sim and some other factors, but the point is some value less than 1. Why is this true? Well, it follows from several things: the simulator mismatch assumption, the low rank MVP assumption, as well as our construction of pi xp. So we can apply these assumptions, do some analysis, and you can show that something like this will. So basically, it just says that if I can't reach some states with pi xp, that means there's sort of like maybe hard to transition to from any state. Like sort of no policy or doesn't matter which state I get into at the previous time step, there's some absolute probability I will transition into these states. Okay, so why is this useful? Well, what we're going to do now is we're going to back up basically one step. So let's now think about rolling in to the states to step h minus 1. And we denote x h minus 1 and x bar of h minus 1 the same as xh and x bar of h. And what we'll do is we roll into this set with pi xp, and then we explore randomly. By randomly, all I mean is just once you get to the step h minus 1, just play actions randomly. Okay. So if we do this and bar x of h can be reached by xh minus 1, then randomly exploring from xh minus 1 will reach it. Okay. If there exists some path from this set of states to this set of states, and I'm just playing actions at random, then it might take me number of action steps, or number of action tries, but eventually I will reach this set of states. Okay, and if xh minus 1 can't reach bar x of h, then that means that the only way to get to bar x of h is through bar x of h minus 1. And based on what we just showed in the first part, this transition can occur with probability at most chi. Okay, so let's do this again. Now we'll back up another step, and we'll think about rolling in pi xp up to step h minus 2, and then exploring randomly from step h minus 2. And we kind of have we can make the same argument, which is that if bar x h minus 1 can be reached by xh minus 2, then random exploration will reach it. And if bar xh can be reached from bar xh minus 1, then randomly exploring from here to here and then here to here will eventually reach it. So again, rolling in to x of h minus 2, and randomly exploring, if x of h minus 2 can reach bar x of h in some way, random exploration will reach it. Okay, and we can do this actually. We keep going backwards for k steps. And what we can say in the end is that either bar x of h can be reached with k steps of random exploration from one of these sets, or it can't. And if it can't, then the only way to get to bar x of h is by going through bar x of h minus 1, bar x of h minus 2, all the way up to bar x of h minus k. And the key insight here then is that each of these transitions occurs with probability at most chi. Meaning that if we're in this scenario where none of this random exploration will reach bar x of h, then the maximum probability of reaching bar x of h is chi to the k. So it decreases exponentially in k, in particular because chi is less than 1. Okay, and so turns out you can just ignore these sets if they're really hard, if the probability of ever reaching them by any policy is less than roughly epsilon. And so as long as chi to the k is less than epsilon, we can simply ignore this. So we actually only need k to be greater than some logarithmic factor. But then the insight here is that, well, if we are exploring randomly from one of these sets, what is the complexity of random exploration? It scales exponentially in the horizon over which we explore randomly. So it scales as a to the k. So complexity of random exploration is not good because it has sort of this large exponential sample complexity. However, the key thing here is that the horizon we need to explore over is only logarithmic in parameters. And so we have to, the complexity is exponential, but the number of steps we have to do is logarithmic. So in total, basically, we get a to the k's polynomial. So the sort of punchline from all of this is that basically by playing pi exp and randomly exploring for a logarithmic number of steps, it's sufficient to reach sort of all reachable directions in Unreal. Once we've done that, once we've sort of collected this data, then we can use this data to learn a near optimal policy in Unreal. And so even though direct transfer doesn't work, and even though actually it turns out just transferring pi exp and playing them by themselves also won't work, if we play pi exp with random exploration, this actually will work. We will actually traverse all the meaningful states in Unreal, and we can sort of use the data we collect and then learn a near optimal policy in Unreal. Okay. I don't know if that was too fast or if there's any question on that, but I'm happy to answer any questions folks might have on how this proof went down.
Any questions here? And also, if there are any questions in the Zoom, please unmute yourself and ask.
I think there's no question.
I can ask another question.
Sure, sure.
I missed how you learn pi exp. So what is this?
Yeah, so I actually the actual algorithm I used for this I pulled from like another paper I wrote previously. The basic idea is you just want to get, so okay, in this low rank MDP setting, we have these phi vectors. So what you want to do is you want to in sim you want to train a set of policies that cover all possible directions of phi. Meaning basically I span my, so phi is within some d-dimensional space. I want to train policies that span this d-dimensional space in sim. And so the algorithm you do this is actually kind of complicated. Again, I just pulled it from another paper. But it basically kind of, what it essentially does is it will just try to, it collects some initial set of states. It looks at the sort of direction that's visited so far, and then it chooses a reward function that basically will try to get it to visit directions it hasn't visited. And you can kind of iteratively do this, and each step of this is just a policy optimization problem. And so we can apply our sim policy optimization oracle to it. And you can kind of build up a set of policies then that'll give you high coverage in sim.
A sequence of reachability type rewards gives you this.
Yes. Yeah. Any other questions?
Okay.
Yes. One question.
Speak out loud.
Yeah. So sort of in the setup we're assuming the sim MDP and the real MDP to have like the same state and action spaces,
Correct.
but in reality, they might like differ slightly. Like, do you think the result could possibly be extended in that setting, or?
Yeah. I think, okay, I guess there's a few ways to answer this question. So, like, if your state space, say, is the space of all RGB images or all proprioceptive states, these state spaces are actually the same. Like, if this, there's this finite set of RGB images, like, if my state space in sim is all of these RGB images, and my state space is real is also RGB images, like, these are actually sort of the same state space, it's just, like, impractically large. So, one answer is just that if you make your state space large enough, you will cover both settings. Um, I don't know though, like maybe another way to think about this is, yeah, so I guess maybe that's the answer I would give, that in some sense, like you can just make your state space large enough to cover both settings. And as long as this low rank MDP assumption still holds over these large state spaces, this is okay. Now, if you're in a setting where like you have to make your state space in a way that like the low rank MDP assumption breaks down or something like that, or you have some mismatch that is not just a dynamics mismatch, like, okay, this isn't looking at partially observed settings, but in practice, you might have some partial observability, and maybe there's more partial observability in real than sim, for example. I think if you sort of add these assumptions or add these modifications, then it's not clear the theory will work. Although what I'm about to show you is like, so we actually ran this in real, and it without, we don't know what the actual assumptions are in real that could be satisfied, but the approach did work. And so I think the theory could break down as you move farther and farther from my assumptions. But I think the algorithmic principle may still be useful.
Yeah, well, question on that. So I guess if you enlarge the state space, would that also have some impact on your sim to real assumption that the transition probability can be bounded? So for basically, if the state is not in the sim, then there's no transition there.
That's a good question, actually. Yeah, very possible. Yeah, I mean, right, like if you have some like state that is actually not realizable in the sim, then you don't actually even have like a well-defined transition out of that state. So I don't actually, yeah, I guess in a setting like that, uh this sort of mismatch could be problematic just in terms of the mismatch assumption.
All you really need is like some kind of correspondence between like the states and the actions. But like, I mean, obviously, practically speaking, it works.
Yeah.
And it feels like theoretically, like if you can establish some notion of correspondence, then
Yeah.
the theory should probably.
Yeah. Right. Like you could imagine, say you had some like decoder or something, right? You can like decode the state from real and map it to what would be sort of a reasonable equivalent state in sim. I think if you assume access to something like that, I think the proof would go through still.
Maybe a related question, can you like change your, I think you have TV distance with something like a bisimulation distance so that you have partial observability in a sense in your sim, but real is not Markovian anymore, and it has some like time varying transitions that still remain close enough.
Right.
Treated as Markovian.
Actually, that's a good question. Yeah, I do feel like you could maybe use some sort of like bisimulation relationship here too. Because the key thing that this assumption gives you is this kind of like reachability analysis. And I feel like some similar like reachability, you could do some similar reachability analysis in a scenario where you had some sort of like bisimulation relationship between sim and real. The techniques would, I mean, the technical details of how this proof went down, I'm sure would differ, but I feel like the conclusion I could imagine still being true. Okay, cool. Okay, so let me keep going. So, yeah, so we did all this theory. We showed that there's actually this provable gap between naive sim to real transfer and sort of this exploration policy transfer. And then we wanted to see if this works. And so what we did, we just ran fairly simple experiments, but actual sim to real experiments. And so we tried to get a robot, this is just a Franca, to push a puck to the edge of the table. And so we trained this in simulation to do this, and we transferred it to real. And what I'm showing you here is that just sort of the standard sim to real transfer, what that got us. It didn't really work, basically. It sort of like, it tries to push the puck, but there's some mismatch that means that the sort of motions that push the puck successfully in sim didn't actually push the puck successfully in real. Okay, and so this direct sim to real transfer in this setting, it kind of breaks down. It doesn't give us what we want. And so then we ran our algorithm and we came up with a way basically to, so again, the low rank MDP assumptions are not satisfied here. So what we did is we just trained, we trained some policy then in sim that just sort of trying to get diverse behaviors. And there's various RL algorithms people have come up with for deep RL that kind of like induce diverse behaviors. We just took one of these basically off the shelf, applied it to learn diverse policies in sim, and deployed these in real. Now when we deployed these in real, what we got some diverse behaviors. Sorry, the video is maybe a bit choppy. But basically the point is these policies did different things. Most of them didn't really solve the task or get close to solving the task. There's one that actually did do pretty well. But the point is when we deploy these policies in real, it makes the robot do a lot of different but still reasonable things. And this gives us a lot of useful data. And so then we took that data and we used that to optimize a policy that was deployed to optimize a policy for real world deployment. And when we did that, what we got was this following behavior. Basically, taking that and optimizing the policy, the optimized policy is able to successfully push the puck to the edge of the table. And so this is still in some ways a relatively simple example. The task is not too complex, but it shows that like this actually did work in practice, that doing this naive sim to real transfer, we got stuck. Doing this sort of exploration policy transfer, we were able to collect a lot richer set of data and use this to optimize the policy. And we sort of quantitatively can show this as well. So in blue, this is sort of the performance of our policy. In orange is the performance of direct policy transfer with fine tuning. And you can see that we're much more able to optimize the reward much more quickly. And I think like we ran this like 4 or 5 times. Every time our method successfully solved the task, and 0 times did the naive transfer successfully solve the task. So this gives some empirical evidence that what we're doing, the sort of exploration policy transfer, is actually able to bias something. Okay. Okay, so that is kind of the first part of the talk. I think I'm running a little bit low on time, so maybe I'll just and I'd like to leave some time for additional questions. This ends in at 3:30, right?
Technically, it
Technically,
does,
yes.
but I think we have the room for longer.
Okay, I'll try to I'll just go through part 2 really quickly and then leave some time at the end for questions. Okay, so part 2 is now we actually make a stronger assumption on the simulator. Okay, so in part, what we'll assume here is that we don't just have a fixed simulator, we have a parametric simulator, and it can be parameterized by some theta in RD. Theta could be something like, say, unknown friction coefficients, unknown mass of objects, things like this. We're assuming theta is probably not super high dimensional, it's a relatively low dimensional set of parameters that can model some aspects of our real. Now, again, so what we assume here then is make a reliability assumption that there exists some unknown theta star, such that if we plug in these right theta stars, sim will actually model real perfectly. Okay, now in practice, this is probably not ever true. So you can really more think of this as sort of basically that you can get your sim to be very close to real, even if it's not maybe truly perfect. And if I can get my sim to be really close to real, or another way to think about this in relation to the first part of the talk is I can make epsilon sim really small by finding better parameters. Okay, so if I can do that, if I can make some epsilon sim really small, then I know that direct policy transfer will actually succeed, as I showed in the first part of the talk. So if I can learn a good theta star, I can just optimize it in my sim with theta star, deploy that in real, and it will solve my tasks. Okay, so in this setting, sim to real transfer actually reduces just parameter estimation. What do we know about parameter estimation? Well, now we can just apply tools from sort of like classical statistics. And in particular, we'll just sort of try to analyze basically parameter estimation rates in terms of the Fisher information. So let's say we have some distribution, pi theta, or p theta, which is conditioned on some pi. In particular, this will be our simulator, and pi will be the policy we play. And let I theta star pi denote its Fisher information. Then if we just sort of draw some samples from this distribution, fit an estimate to it, sort of known results in statistics, this is just like actually the Kramer-Rao lower bound, say that under some conditions, the mean squared error by parameter estimate is lower bounded by the trace of the inverse Fisher information matrix. Okay, so this just says that like how quickly I can estimate these unknown sim parameters if I'm playing policy pi in real to collect observations is governed by sort of the inverse Fisher information matrix. Okay. So then this really suggests that, well, what do I want to do to estimate theta star? I should just play a policy in real, say pi exp, an exploration policy, that minimizes this inverse Fisher information matrix. Now, the challenge here is that the Fisher information matrix differs for different thetas. So for any given theta, any given simulator with distribution p theta, I can calculate its Fisher information matrix and compute an exploration policy minimizing that Fisher information matrix, or maximizing the Fisher information. I don't actually know what the true parameters are. And so you sort of have this kind of chicken and egg problem again, where you want to sort of like you want to explore in real, but you don't actually know something about real, or you don't actually know enough about real necessarily. And so we rely actually in this paper on the same basic idea from the previous paper, which is that even if I can't transfer a policy that will directly solve my task, I can still often transfer an exploration policy. So for example, say this task is picking up the block, an exploration policy might look like the following. It just kind of like pushes the block. And what this will do is it will basically help me to figure out how this beam behaves. And if I deploy this in real, it might not be able to successfully pick up the beam, but it can still easily push the beam in real. So it's easy to transfer a policy that'll just push the beam in real, and that will tell me something about this unknown parameter. In this case, the parameter is the location of the center of mass. And then I can deploy this policy in real, learn something about the parameter, fit the parameter, and then optimize in sim. Okay, so this is basically what we do. I'm just going to show quickly some results. Basically, if you just try to do direct transfer, this is actually even with some domain randomization, you won't, sorry, the video is a bit choppy again, I think, but you don't succeed most of the time. What we can do though is we can basically optimize a policy that explores in SAM, which kind of will just push it around the block. And if we do that, we take the learned parameters, we add those to real, or add those to the simulator, optimize a policy in the simulator, what we get is that a policy that will mostly succeed. Okay, so I think in this example, the direct transfer succeeds 6 times, and this in our method succeeds 5 or 6 times. Okay, so in some sense, this is actually like fairly standard. I mean, this is basically just system identification, what I showed you. But a sort of thinking about system identification in the context of the sim to real, and how I should basically learn exploration policies in sim that will sort of like help me speed up my system identification. And so we implemented this on various tasks, this sort of block stacking one, some others involving like pushing a puck, and we found in general that it worked. Okay, so just to wrap up, going back to this question I started with, how can we utilize simulators to speed up real-world RL in settings with large sim-to-real gap? What I've argued is that in both settings, in both realizable and unrealizable setting, you want to use your simulator not to learn to solve the task, but to learn some exploration policies that can efficiently collect data in real, and then use the collected data in real to learn to solve your task. And we saw that this basically enables efficient real-world RL across a variety of different robotic manipulation type tasks. Yeah, so I will end here and happy to take additional questions.
Thanks, our speaker. I have a question on the chat box. So regarding the first part of your talk, did you also compare the exploration policy versus the domain randomization as well?
Yeah, so the experiment I showed you in the first part of the talk, with this this experiment, actually in sim, the sim policies were trained with domain randomization. So our theory doesn't cover domain randomization because we just assume that we have a fixed simulator, which is not randomized. So there's no parameter to randomize. But when we actually deployed it, we did do domain randomization over the parameters of the sim. And so even with domain randomization, it still didn't work.
Any questions in the room right now?
Yeah, I'm just wondering, like, have you experimented with like more complex manipulation tasks to see if there's any benefit there? I know it's still kind of hard to do that in general.
Yeah, we haven't. So I guess the most complex tasks we have are like, at least the real world tasks are from the second part of the talk where we were looking at more or less like balancing objects on top of other objects. This other task we had involves like basically pushing a puck, sort of like playing shuffleboard, like can it sort of hit get the puck to the target. Those are the most sophisticated tasks we looked at. I think it would be very interesting to test this with more complex tasks. We just didn't. Yeah, we just basically ran out of time for the deadline and then haven't sort of come back to it. But I will say it kind of did just work. At least the approach from the first part of the talk of transferring these exploration policies, it kind of just worked on the first try. So I'm optimistic that if you applied it to more complex tasks, it would also work. However, certainly as the complexity of the task grows, like, it's going to become more challenging. And maybe you have to do more sophisticated, learning approaches too. So, yeah.
I have a question on your first part, the experimental results. So it kind of like seems your proposed approach have a larger variance compared to just directly transferring the optimal policy based on the figure you showed.
Sorry, can you say that? I kind of missed what you said there. Can you say that again?
In your first part, based on the experimental result, your proposed approach seems to have a larger variance. Is that correct?
In the first part of the talk.
Yes. For the
Are you talking about you mean like in terms of just the error bars?
seem to have a larger confidence interval. Can you comment a little bit on that?
Yeah, so I guess the basic reason for this is that just the direct transfer didn't work at all. So it just failed every time. And so the variance for direct transfer is very low just because it didn't do anything interesting. So ours does have a higher variance just because like if you looked at sort of the individual learning curve, they're not all learning at exactly the same rates. Whereas direct policy transfer kind of like didn't learn for every single attempt. So that's kind of the difference in variance. I guess maybe the bigger question here is like if they both solve the task successfully, which would have lower variance. I could imagine in that case that if direct transfer does solve the task, it would have lower variance, just because our approach does sort of by design, it produces a set of policies that produce sort of high variance data. And so this might lead to greater variation then in the policies you learn on this. Yeah. So you might have somewhat of a trade-off there, but again, the benefit is that you often actually are able to solve the task where direct transfer won't.
Thank you. I think there's no more questions. There's a question from the thank our speaker again. Thank you, Andrew, for accepting this invitation.
Yeah, thanks again for the invitation. It's great to share this work. Feel free to email me if there's additional questions on any of this.
Great, thank you. Yes.
Okay.